The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody, and this is Dr. Mansour, and today is June the 7th, and this is the Seismic Review Workshop, and as you know, this is the second quarter, and if we go to the second quarter schedule, you will find that here we go. Today is Sunday the 7th from 1 to 5, and we still have two more sessions coming on the 21st and on the 28th. And I don't know how many of you are taking the exam very soon. I don't know if the Prometric, they already start open the exam sites. Please let me know, and if you have any question, you are very welcome to ask, and if you need any additional session to help you to prepare for the exam, I will be glad to do that. As you know, I taught this class in the first quarter. This is the second quarter, so all of you have access, those who are enrolled in the class in the spring of the first quarter or the first quarter of the spring. You have access to the 55 hours on demand, and this is available for you 24/7. Here you will find that I have 28 hours live workshop or workshops to go over the problems and the concept or whatever you are need me to go over. In the spring, when I was teaching the class, the last lecture, chapter 15 and chapter 16, for some reason the recording was not, we have an issue with it. We don't know why. My staff and also the company that we are loading their, we're loading our recording on their server, they were not able to solve the issue with the recording. Recording was bad or defected for whatever reason is. So I mentioned last time that I will be recording again the chapter 15 and chapter 16. I will go over them today first, and after that I will ask my staff to take this recording and add it to the on-demand, so the on-demand will be complete in this case. Okay. After that, I would be glad to answer any other questions related to any chapter or any material or any problem, either from the textbook or from the 626. And I hope that all of you already loaded the software, and if you have any technical issue, please let me know. This is the most comprehensive book available in the market as far as I know. I'm doing all my best, and please let me know if you do have any question or any concern about any material. If you believe there is any typo or mistake or an error, normally when I come up with the new edition, this is the 5th edition. So any statement that you believe that it does have a concern, I will be glad to go over this. So chapter 15 and chapter 16, those are the last two chapters of my textbook of the Seismic Design for a Professional License. I will go over them, and after that I will go over problems and listen to your questions and so on. Chapter 15, the title of this chapter is Structural Damage and Retrofit. And this chapter is based on the Applied Technology Council ATC 20 and ATC 20-1. Those are the two references listed by the California board, the procedures for post-earthquake safety evaluation of buildings. This is the ATC 20, and the other one, it is ATC 20-1, the second edition. They came up with a second edition. This is a field manual for post-earthquake safety evaluation of buildings. So by Applied Technology Council, ATC. I highly recommend you to buy these two references, and I mentioned this before, but as a reminder, please do your best to locate them or buy them as soon as you can, and we will I will touch some stuff from these two references. Already I extracted in my book some drawings or some illustrations from these two references, but obviously I cannot extract everything. So I really appreciate if you, secure these two references as soon as you can. Okay, so here are the topics to be covered in chapter 15. Failure and seismic retrofit of existing utility pipes and tanks. Structural damage due to earthquake. We are going to talk about different situations where you have a damage that has occurred due to an earthquake. Like unbraced equipment, unbraced ceiling systems, unusual building types, poor anchorage cladding, poorly reinforced concrete walls or columns, unreinforced masonry walls, the URM, and poorly walls poorly anchored to floor and roofs. Those are topics that will be covered. And after that, we will go to examples from the ATC 20 for different types of structural damage. We're talking about the wood frame structures, concrete frame structure, flat slab, steel frame structures, precast concrete and concrete shear walls, tilt-up masonry, and at the end we're going to talk about the seismic retrofit of existing structures, and finally the seismic retrofit of California bridges that has been occurred or that has been implemented after all these earthquakes. They found that we need to go back again and retrofit or increase the strength of the existing structures because they are lacking strength in order to resist the earthquakes with minimum damage. So if you flip the page, chapter 15, and this is from my 5th edition. So seismic retrofit of existing pipes and tanks. If we do have a pipe, either underground or above ground, these pipes could be subject to an earthquake event, and in this case, if it is in a seismic zone or a seismic area or seismic design category, that we do have seismic events. So we have to secure these pipes such that if an earthquake happens, the pipe will not damage at all or suffer minimum damage in order to maintain the integrity of the pipe. So pipes above and below ground. When considering or when constructing pipes, crossing an active fault. So we do have an active fault, and we have the pipe is crossing this active fault. So the following parameters should be considered. So I do have an active fault, for example, here, in this illustration here, assuming this is an active fault. As you can see, I drew it that way. So we remember from chapter 4 the types of faults. It could be right lateral or left lateral. So if you stand here, this is going to your left. If you stand on the other side, goes into your left. So the illustration here that I'm using, this is a left lateral fault. And the direction, by the way, is very important in this chapter, as we're going to see in just a minute. So we need to know which fault type he is talking about. So when you see a problem, please pay attention to the type of the fault. It is left lateral or right lateral. If the fault is normal or reverse, and so on. So if this is a pipe that that's crossing this active fault, as you can see here, so we need to make sure that this pipe is secured enough such that if the fault start to move in any earthquake event, so the pipe will be secured and will not be damaged. So in order to do that, we need to consider the following. Number one, the orientation of the pipe with respect to the fault direction, the fault displacement, the amount and the direction, the type of the backfill material for underground pipe or underground pipes. When we have pipes underground, under OG, so when we put a pipe underground, we have the trench or have the cut and put the pipe and put some material under it. It's called bedding material. The backfill, the material we are putting here is very, very important. We need to make sure that this material will allow the pipe to move freely. There is no any constraints or any restraint on it. So this is something very important as far as the backfill material, which in this case, a backfill material for underground pipes. Backfill material, the type of the material is very important. The type of the pipe, if the pipe is going to be constructed from concrete or plastic or any other material, and the type of the support and anchorage of the pipe above ground. Also, the pipe, if the pipe is above ground, so like this scenario here, this is an active fault, and also I draw it to be left lateral fault, but it could be any direction. Okay, so when you have this pipe here, we need to ensure that this is a pipe above ground. This is a pipe above ground. So the pipe is running this way, and in this case, it is normal to the fault. So we need to make sure that we have some kind of flexible joints. These flexible joints will allow the pipe to be move, okay, as the fault moving or the fault is slipping either right or left. So this is something that we need to, so flexible joints, we need to provide flexible joints in order to allow the pipe to move in case of an earthquake event. Those are the parameters. So I need you to be aware of these parameters just in case if they ask you on the exam, which of the following parameters should be considered or should be taken into consideration when we are constructing pipes above or below ground, crossing an active fault or near active fault. Sometimes also the word or near or crossing. Okay, when an underground pipe supported by sand or clay crossing an active fault at or near perpendicular, the pipe most likely to fail due to shear stress. Let me remind you in chapter 3, we talked about different types of stresses. Chapter 3, stresses, because we need to know what type of stress will cause failure. We know stresses, it could be normal stress, normal. We use the letter sigma, Greek letter sigma, and this normal stress could be either tension or compression. And we use sigma T for tension and sigma C for compression. Like the famous tension test that we did in school, the famous steel specimen, and you apply a tensile force and we can determine the value of sigma as B over A, where A is a cross-sectional area perpendicular to P. This is a requirement for the normal stress. The area must be perpendicular to P. This is an example of the tension test that we did in school. So we have tensile stress. The other normal stress here is sigma compression. Also in school, we did the compression test for concrete. This concrete cylinder, the 6-inch by 12-inch. And after we cap it with the sulfur compound, we apply the load. And also still sigma is equal B over A. And the A is a perpendicular to B also. If you remember in concrete design, we call this F sub C prime, the 20-day compressive strength, as we discussed also before in chapter 12. So both of them are called normal stress. The second type of stress that I need you to be aware of is the bending or flexure stress. Bending slash flexure stress. This type of stress, which you call it bending or flexure stress, it does have, if you look here, you will find that the entire cross section here, it is under tension. The entire cross section here at any point here is under compression. That's why we sometimes we draw the stress to be like this. It's uniform stress, except in the vicinity of the load where we have a stress concentration. The same story, the stress here also, it is uniform and it is tension. So we have the entire cross-section of the member subjected to either tension or compression. For a flexure stress or bending stress, like beams, can take a simple beam and whatever load or loads. So you will find that we have two types of stresses. We have the tension and compression occurring simultaneously. So this compression and tension. So whenever we have a member subjected to tension and compression at the same time, we call it bending or flexure stress. And the famous equation, as you remember, sigma is equal mc over I to give the maximum, or the general equation sigma is equal my over I. And also these equations are given in chapter 3. There is a table summarizing all these types of stress. So this is called bending or flexure stress. So the third type, we call it shear stress. Shear stress. And we use the Greek letter tau. Tau is also B over A. But what's the difference between B over A here and B over A here and B of A here? Here, the area in these two types of stresses, the area must be perpendicular to B, normal to P. But the shear stress, the area is parallel to P. Okay, example of that, if you have two plates, and these two plates are connected together with some kind of bolt or rivet, and this is the force, and this is the force P. So in this case, the area we are talking about, the cross-sectional area of this bolt here. This is a bolt or rivet, and you will find that the area of the bolt is, this is the area which is parallel to B. You see, it's not perpendicular to B. So this is a huge difference between shear stress and normal stress. This is a shear stress, and this is a single shear stress because we have a only single shear plane. This is single shear stress. Double, we are not going to talk about it here. Single shear stress. Okay, this is what I need you to remember from the types of stresses that we discussed it way back in chapter 3. The statement that's mentioned in chapter 15, and let me take you back to the chapter 15. I am on page, by the way, 454, based on my 5th edition textbook, page 454. The statement says that when an underground pipe supported by sand or clay crossing an active fault, strike, slip, fault, at or near perpendicular angle, the pipe most likely will feel by the shear stress. Let us draw this scenario. So if you have a pipe underground, so after we open the trench and put the pipe and put the material, we'll cover it. So he's saying that if we do have an active fault, this is an active fault, and the pipe is crossing this active fault at an angle almost near to be perpendicular. This is a pipe here, which is this pipe here. If we put the material around this, like sand or clay, any kind of material like this sand or clay material will not allow the pipe to move freely. So in case of a lateral fault, like this one here, right or left, so this exactly like the shear stress here, two forces, equal magnitude, opposite direction, and they are going to shear this. So this pipe here most likely will fail by shear stress. You see that? See an analogy between this and this? So in this case, for an underground pipe, and instead of putting sand or clay around this pipe, because the sand or clay will restrain, will prevent the pipe from any movement in case of an earthquake. And this is why the second statement will illustrate that, saying that a wide trench or loose granular materials will reduce or eliminate the shear stress action. So instead of doing this, and I have the pipe, I will have, so this is not the best way to construct this pipe. So in this case, we are going to have the trench also, whatever the size of trench based on the size of the pipe and the OSHA requirement and stability and all these things. So in this case, after I put the pipe and I put some kind of material under it to protect it from any settlement, because normally you put some material under it, it's called bedding material to support this pipe. So in this case, we have two options. Either let this a wide trench without any supporting material around it, or we can put loose material. Any loose material that allow, if the pipe start to move, the materials around it, okay, it will not be restraining this pipe. So it's not compacted material, loose material. So we need to be aware of that when we are doing the pipes underground. Either a wide trench, or if you like to put some material, put material such that it allow this pipe to move freely by putting some loose material, okay, not necessarily to be dense as a sand or a clay. It could be some kind of, okay, very light material. Sometimes we put very light material like the loose aggregate, okay, pumice, it's called pumice, very light, and we can do that. Or if you like to leave the trench, so in this case you have to make some kind of support here, such that if you like to bring everything back again to the OG, so in this case you are put some kind of cover, either a steel plate or whatever system you like to do. If you like to leave this trench to be open, wide, to allow this pipe. So this is the desirable, and this is not the desirable one. I need you to be aware of that. This is a figure 15-1. Figure 15-2, retrofit of underground pipe. For example, if this is an existing system here, a pipe, and maybe we talked about liquefaction before, by the way. Liquefaction, as all of you know, faction is a sudden drop in the shear strength of the soil due to the water table, due to the presence of the water or the poor water pressure. Liquefaction is defined as a sudden drop in the shear strength due to the poor water pressure, And this was discussed before in 2 different chapters. So I needed to remember. So in order to prevent this pipe from fail because of the liquefied soil, we can anchor it. Okay, it will hold the pipe in place, but it will allow some kind of movement. We have no problem with that. So in this case, we can provide some kind of anchor, okay, such that the anchor should provide some kind of flexibility, okay, so the pipe can move, but the poor water pressure or the liquefaction action will not damage the pipe. And in this case, we can protect the pipe. So if you flip the page, you will find that series of illustrations. One of them already mentioned. So underground pipes crossing fault at right or left lateral fault nearly perpendicular. This is the one I was telling you about. Underground pipe, probably this word extra here, probably underground pipe crossing. This will be the best. Okay. Underground. So this is the OG is here, and this is a pipe, and this is what I was talking about. So if we do have this kind of fault, okay, either right or left, it does not make any difference. And if this is a pipe, the one shown here, okay, let me color it. This is a pipe, the underground pipe. So the possibility here, or the stress that will cause failure, is a shear type failure. Here it is, shear type failure. So this is shear type failure. Now we are going to take above ground. And I have 4 cases: above ground pipe, crossing an active fault. So if this is a fault line, and if this is a fault line, and the orientation of the pipe is very important to know where is the pipe with respect to the fault line. And they should give you the picture, by the way, or they describe it very well. This is a pipe, and this is a pipe. So this is a pipe, and this above ground. And you will find these 2 cases, and if you flip the page, you will find another 2 cases. I will talk about these 4 cases, but we need to pay attention to what type of stress will cause failure. Let me remind you of something from statics, because this will help. In statics, we learned there is a force, a slanted force or an inclined force like this, F, can be resolved into 2 components, F sub x and F sub y. So F is the resultant of these 2 components. So if this is the angle theta, we know F sub x is equal F cosine theta, and F sub y is equal F sine theta. By doing this, I get rid of the original force, and I resolve the force into 2 components by breaking this resultant into one in the x direction, one in the y direction. This is called resolving a force into components. Resolving forces into components. A single force can be replaced by the 2 components. We are going to use this concept here to decide if the stress will be compression or tension. And this is the first figure here, figure 15.4. So if I have this orientation, I have this fault here. What type of fault is that? As we said, that you can stand on one side of the fault and look to the direction. So this is the left lateral strike fault, or strike strip fault, if you like to give the full name. This is a left, okay, so because I'm standing here, and this arrow here is to the left, to my left. If I'm standing here, also this arrow is to my left. So this is left lateral fault, left lateral fault. What will happen if the pipe is crossing this left lateral fault at an angle like this, small angle, call it acute angle? So I am looking right now, this is the force I'm referring to, the force that will come from the fault. Here it is. I can resolve this force into 2 components, one along the pipe and one perpendicular to the pipe. And this is what the 2 components I'm talking about, F sub x and F sub y. If I put my coordinate system like this. If you like to reverse it, it does not make any difference. If you like to make this is Y and this is X, it does not make any difference. Okay? So you will find that this force is this way. So these are the two components. And the same story, if you look to the other force, it's coming this way, which is the other arrow here. You'll find also I have two components, one this way and one this way. So if you look to this F sub X and F sub X, when you have a member subjected to these two forces here, like the cylinder I was referring to, what kind of stress is that? This is a compression. And this Y here, compression type failure. Do you see that? Let's take the case number 2. This is case number 1. And in my 626 book, you will have some problems. I can grab these problems immediately after we finish this. If you look to case number 2, I still have a pipe shown in yellow. And I have here this, what kind of fault is that? If I am here, standing on the side of this fault, is still to my left, so it is left. If I'm standing here, this also is still to my left. But the orientation of the pipe, instead of this direction, the pipe has been at a small angle. Also, the issue here is a small angle. Because as the angle gets increased, you will find that we have shear stress. I will do the same thing. This force here can be resolved into two components, F sub X and F sub Y. And the same story with the other force that's coming from the fault movement. So I have F sub Y and F sub X. If you look to the two forces acting on the pipe is still yellow. Let me color the pipe also. This is a pipe, and this is also the pipe here. But just I enlarge it to illustrate to you the concept. So these two forces are pulling like my tension here. So these two forces are pulling the member. So in this case, it's going to be tension type failure. So far, so good. And this is why on the top of this page, or at the top here, say that a pipeline above the ground, parallel or nearly parallel, subject to so and so, it will result, okay, either tensile or compressive. Parallel or nearly parallel to the fault. This is the pipe is not parallel, nearly parallel. It is a small angle. Okay. If you look to the case number 3 and number 4 on the following page, we will see something interesting. This is the case number 3. Again, I have an active fault. And we do have the pipe crossing the fault at an acute angle, a small angle. And this is the pipe here. So if you take this force here and find the components replacing this force, you'll find there is one force this way and one force this way. And the same story with the other force that generated from the direction of the fault. So I have F sub X and F sub Y. These two forces are pulling the member, so it is tension. So what's the difference between this and the previous one? You'll find this type of fault is what? If I'm standing here, this is to my right. If I'm standing here, is moving. So this is the right lateral strike fault. So this is the right lateral strike slip fault, or just simply say slip fault is sufficient? Or if you like to write the entire name. And this is case number 3, so it is under tension. And finally, case number 4, that I have the pipe has been oriented opposite to what shown before, and the fault is still considered a right lateral fault. I am here, so this is the right lateral fault. If we do the same thing, you will find that this force can be replaced by 2 components, and this force can be replaced by 2 components, and this force shown compression. So I have here compression, I have tension, the previous case, and so on. So it is very, very important to know, in order to analyze the pipe and determine what kind of stress, because he will ask you what kind of stress, the stress causing failure, the stress causing failure. Two things that you should pay attention to when you examine and decide which stress will cause the failure. Number 1, the type of fault. Number 2, the orientation of the pipe. Orientation of the pipe with respect to the fault. Or let me write it on the, because this is, so the stress causing failure for pipes so we need to the type of the fault or fault type and the orientation of the pipe with respect to the fault or in relation to the fault. And I will add another item because we saw different types of stresses, tension and compression. This is tension, for example, figure 15.6, this is tension. Figure 15.7, it is compression, and the previous page we have also 2. So as you know, some materials, they are strong in tension, and some materials are strong in compression and weak in tension. So I will add also in addition to these 2 important parameters, I will add the material type, which is mentioned at the beginning of the discussion, the materials that will be used to manufacture the pipe. For example, concrete, as you know, is very strong in compression, very weak in tension. So the concrete, as we remember from the stress strain curve, concrete epsilon, and this is sigma. This is the stress strain curve for concrete that came from the cylinder test, where this is F sub C prime. So the concrete is very strong in compression, and very weak in tension. like about 10%. The tensile strength of concrete is about only 10% of F sub C prime, maximum 15%, and even the 10% or the 15%, the ACI code is ignoring that. So the material is very important. Steel obviously is different story. Steel is a strong in tension as is in compression. So the stress strain curve for steel under tension and compression essentially the same, by the way. Probably I drew it before. Let me show it to you one more time. Probably I did that. Epsilon, and this is sigma. Okay. So if this is under tension, the stress strain curve under tension for steel, and this is the modulus of elasticity E, as you remember. This is steel. Under compression, the stress strain curve is a mirror image, by the way. Here it is. It's like that. This is under compression. And this is under tension. Concrete, this is under compression. If you look to the stress strain curve for this material under tension, you'll find it's very small. Here it is. That's it. This is under tension. Because we know concrete is very weak in tension and strong in compression. So when we study or examine the stress that will cause the failure for whatever pipe crossing an active fault, so we have to consider also the material and decide which material will be best in order to resist this and resist failure. So I need you to be aware of that. If you look to the 6-6, my textbook here, which I assembled all the problems I have over all these years, you will find that, and please let me know if you have any concern about any problem, and I hope the CBT is working fine with you, the computer-based test program. I believe there are a few problems at the end somewhere here. Let's see if I can locate them. If not, I believe you can. I know there was a drawing, and here we go. Yeah, I found them. Still remember some stuff. Here it is. A problem 340. If you have the 6-6 book with you, the CBT seismic. If you look to this problem here, problem 340. If you don't have the problem or you don't have the book handy, here it is in front of you. Let us try to answer this question in relation to or based on the discussion we just mentioned. Do you have a drawing? So either A or B or C, and you can see the answer A, he gave you both the bending and the flexure stress. A new water supply line to be constructed above the ground. And we have a left lateral strike fault. So if I'm standing here, this is coming this way to my left. If I'm standing here, I show both arrows, but if you're standing here, it should go to my left. So this is the left lateral fault, and this is a pipe. And the other arrow this way. Normally, it will be much easier if you draw only one arrow, but it will give you the same. So do you agree with me that this is a tensile stress? Okay. If you flip the page, you'll find there is another two problems related to this. You might say, wait a second. This is the same drawing as before. Okay. This is the same drawing, by the way. If you look to the previous problem, and the reason for that, I will tell you why I did that. This is, it is the left lateral strike force, the one we just talked about. Here it is. If I'm standing here, is to my left. If I'm standing here, is to my left. So this is the left lateral force as drawn. But he mentioned that the pipe will cross so and so and so. If the same above ground lifeline, but the active fault is a right lateral fault. So this drawing, it does not reflect the last statement here. It will give you this is a pipe showing under the left lateral fault. What will happen if the fault is a right lateral fault? So here is the active fault, and here is my pipe at this angle here. And the fault in this case is right lateral fault. So if it is here, if I am standing here, is to my right, going this way, opposite to this. If I am standing here, it is to my right here. Okay, so I need you to pay attention that the drawing not necessarily to be reflecting portion of the statement. He changed the last thing, that if the fault is right lateral fault. And finally, right angle. Probably in the future, instead of confusing you, probably he said that a new water line to be constructed above the ground in an area having a left lateral fault. The pipe will cross the fault at an angle this and so and so. If the same ground lifeline shown crossing the active fault at almost right angle, and the supports of the line are spaced outside the fault trace. What is a fault trace? Each fault, it does have a fault trace, a certain distance. And there is a definition for that, by the way. In the previous code, we talked about it. So it is a fault trace, mean that there is an area, and they define it for us, by the way. The code defines what is a fault trace is. Okay, don't worry about it. So like the boundaries of the fault. The fault is, they go a certain depth, and the fault, okay, a trace, it is a distance on each side of the fault. So it's called fault trace. Fault trace. So if the pipe is crossing at right angle, so now, if you want me to draw this right now, here is the pipe. And it is a crossing, or either, let me fix the fault and change the pipe direction. Let me change. Keep the fault. Okay, it doesn't matter. He called left, so if I'm standing here, it will be to my left. If I'm standing here, it will be to my left. So this is a left lateral fault. Left lateral fault. And assuming that the pipe is crossing the fault at almost 90 degrees. Almost. Almost 90 degrees. So this is a pipe. And the fault has a fault trace. Let's assume that the fault trace is like this. This is the fault trace. And we put the support for this line outside. So the support for this pipe, both of them are outside. And normally these support, by the way, we make them loose such that when the pipe start to move due to the fault, either this way or this way, in this case this way, this is pushing this way and this other was pushing, so it is this way. So there is some kind of, these are the support, and this is the support. So in this case, what is happening to the pipe? In the event of fault rupture, the fault became active, the stress causing damage of the water line is, so this is above ground, almost normal to the fault. It is the left lateral fault, but we put the support outside the fault trace. Because the support outside, and he should add something here, probably the supports it have some kind of flexibility. or some kind of room for movement. But if you mention it like this, also I'm still picking the answer A, the line less likely to be damaged, because I put the support outside the trace, and it will move a little bit this way in this case. And in this case, the best answer is going to be, but if the pipe is completely restrained, if the pipe is completely restrained, okay, it could be shear stress, by the way, as we indicated before. Okay, and I try to explain these things also. If you look to my solution, you'll find that I provide for 341 and the 342 and 340. Look to these three problems because I need you to be aware of these types of questions, just in case if you are having any of them. Okay, so those are the cases I need you to be aware of, and please let me know if you are. Tanks. Existing tanks, like this one here, when they are subject to a seismic force, these tanks, whatever liquid inside these tanks, if you remember, there is something, we talked about it in chapter 8, sorry, something's called slushing force. Slushing force. This inertia force is going to be, okay, causing a lot of damage. And this is why we have something called the freeboard. If you remember the freeboard, I can show it to you right now one more time. Freeboard, there is a table. So tanks, existing tanks, ground motion due to an earthquake causes inertia forces of the liquids inside the tank. The combined ground motion and the inertia forces, okay, put stresses on the wall tanks of the walls, okay, of the tank, the foundations, and the anchorage of the tank to the foundation. So we have some kind of foundation here, and this tank start to move back and forth. So if the inertia force in this direction, so this will be uplift force, and this will be, okay, compression. So this is tension and this is compression. So the compression force is trying to make buckling. You remember buckling from columns? Buckling. So you'll find that the wall is going to be buckled under the compression force. So the tank was like this originally, and whatever the foundation is supporting that. So when we have the tank start to move under the effect of an earthquake force, if the inertia force in this direction, so you'll find that the pipe or the tank will be tilting this way, where this side will be tension and this side will be compression. This compression force will make these walls like this. It will buckle under the effect of the compression force. And the same story for the other direction. Okay, so obviously the anchorage between the tank and the foundation, this is a foundation. We need to make sure that the anchorage is strong to prevent this uplift force. This is uplift. Do you remember the uplift force? We talked about the uplift force in more than one location. So I needed to be aware. In order to improve or increase the strength of the tanks, we do retrofit. Retrofit means that increasing the strength of the existing. So if this is an existing tank, as is here, and these are the walls, and normally the walls are not constant because the bending moment at the bottom is the highest. So this is why the tank wall. It could be variable, as you can see. And this is the foundation, the slab, concrete slab. So in order, this is the existing one. In order to increase the strength of this tank, we do some kind of retrofit. You can put a stiffener plate. A plate will strengthen the tank wall here, because we're here at the maximum bending moment. And we can put an angle, and we put an anchor bolt. So a stiffener plate could be added to increase the strength of the wall. And we can weld this angle here to the steel plate or the stiffener plate, and we can anchor this into the foundation to prevent the uplift. Like hold down. Do you remember the hold down? We talked about it in the class. Hold down for all structures. We talked about this here, the hold down, where you attach this to the vertical studs, and this is to the sill plate. So the same concept, but here we are using an anchor bolt in order to anchor the tank to the foundation. So this is the kind of retrofit that normally done. So far so good. So pipes and tanks are, if you flip the page, you will find the ETC 20 and 20-1. What is the purpose of these two documents? These two documents are giving the guideline for us after an earthquake event. After an earthquake event, we need to decide if the amount of the damage that occurred, how much damage, and what is the condition of the facility. It is accessible or not, or should we shut it down completely, or what? So probably some of you attending this training, so as one-day training course, you can be certified as an inspector. You can go and inspect buildings after earthquakes, and you decide what is the condition of the building, and you take the necessary action if you allow anybody to go inside the building or not, or what kind of action should be taken. So this is the purpose of that, of these two references, which I told you, please try to get them. So safety evaluation and the example of structural damage due to earthquakes were ETC 20 and 20-1. I tried to summarize these two documents, and I extracted some illustrations to show you the typical damage that you see. So there are three safety evaluation procedures within ETC 20. One is called rapid evaluation, and the other one is called detailed evaluation, and the third one is engineering evaluation. And I put them in this table here. After I provide a brief summary based on the description given. For example, the rapid evaluation, typically 10 to 30 minutes per building, is the first and many times is the only safety evaluation performed. These evaluations are often cursory in nature because there are insufficient personnel available to perform more thorough investigation. But if we go to the second one, which is a detailed one, it takes about between 1 to 4 hours. Visual examination of the damage, and so on. The engineering one, it takes, you see, 1 to 7 days. Why? Because is going to be look to the building, and you have to do an evaluation based from the engineering point of view. Do some analysis, do some kind of calculations, writing a report, and so on. And these three types of safety evaluation are summarized in this table here. Either you can read the brief description before, or you 10 to 20 minutes. Here it says 10 to 30 minutes. Close enough. I can look at it to see if which one is the more accurate. But I doubt that they will ask you to do anything like that. But it will not hurt to be accurate. I will look at it and see which one is the more accurate. I think the table is something similar to this. I will look at it during the break. I don't like to. 10 to 20 minutes this is correct. So probably this could be, so I prefer to make this also 20 minutes to match, because this is correct. I verified very quick. Okay. Yeah. So, and as far as who is required, who is qualified, or the personnel required, or required personnel to do this analysis, they are giving us, or evaluation, sorry, much better word, evaluation. So, for example, the rapid evaluation, qualified building inspector, civil structure engineers, architects, other individual deemed qualified by the local jurisdiction. So this is the, and also what is the goal from each type of evaluation. Okay, so I need you to be familiar with these three. They also shown here in a form of a flow chart. Sometimes the flow charts could be much easier to follow or much easier to grasp the concept. So, structure identified for evaluation, rapid evaluation, okay? And when we do this, it is building, if the building, it seems okay, or questionable, or obviously unsafe. If the building is unsafe, we post, and there are some colors you are going to see shortly. So it is post unsafe. It is a questionable, you post limited entry. And if the building, it seems okay, so you say that posted, okay, you are going to post inspected, and that's it. Okay. As far as the limited entry, you need to go and examine to see what the condition by doing detailed okay, and you will find that there are different chapters in this document, and I highlight or I recommend you to put some tabs because during the exam you need to know, for example, this is chapter 3, general procedures for building safety evaluation. And after that, they start to talk about materials one by one. Okay, let's go to a certain material here. Okay, for example, let's take this one here, which is chapter 6, inspection of wood frame structures. They are telling us when we go and evaluate or inspect a wood frame structure, what should we look for? And they give us some examples of pictures. This one here, this is a figure 6.1 they are showing, and I have this picture, or I have this drawing here, and they are taking some pictures, by the way, showing the damage. Okay, so here it is. Home with damage, a cribbled wall or a cribbled wall. Cribbled wall, if you remember, I gave you the USB that I sent it to you, or we send it to you. It does have a movie. I don't know if you watched the movie or not, how to strengthen this cribbled wall. Okay, the cribbled wall, it is the wall, okay, short wall, and we're supposed to examine this, and we can strengthen the cribbled wall by adding some uh, plywood or OSB. And I encourage you to look to the video, the one does have. So each material, and they give you different examples, by the way. Here it is. This is open front apartment with severe damage. As you can see, these are, if you remember, the different types of irregularities. We talked about one of these types, by the way. If you get closer to the picture, close up parking, okay, area of apartment building, vertical support, as you can see here, is completely damaged, and the cracks and so on. So this picture, they might give you an illustration or a situation, and they'll tell you, okay, what should be done. And the same story for masonry and for steel and so on. So what I did, I took some illustrations from so they have the chapter here, by the way, chapter 6, chapter 7, and also. So I need you to, after you purchase your copy, or if you have a problem, please let me know, I can help you. And we can, okay, I need you to put chapter 10, inspection of steel frame structures and so on. Concrete structures, tilt up structures is a serious type of structures, or structures that has serious type of damage, because tilt up, basically, we're going to see it in just a minute. These are the precast element. They bring it to the job site and they assemble them. So the connections always is an issue for the tilt up. So they give us all these things. So if you follow this chart, you can say that if it is inspected and it is unsafe or safe, at least to give the public, okay, peace of mind. So if you flip the page, you will find that on page 460, and specifically table 15-2, you will find that the building safety evaluation classification, we have inspected, and this is the green color. Limited entry, we are using yellow, black, and if it is unsafe, it is red. I need you to be aware of these colors, and because sometimes they ask these questions, what kind of color of the black or the board or the sign that you put. And inspected, and here is description, no apparent hazard found, although repair may be required, original lateral load capacity not significantly decreased, no restrictions in the use of in use or occupancy. So inspected, and we found it's good, so put a green. And the yellow, it is limited, and this is the description what is limited mean. And red, obviously, it's unsafe, extreme hazard, okay, imminent danger of collapse from any aftershock. So it is unsafe to enter, okay? So I needed to be familiar with these three colors, the green and the yellow and red. Example of boosting and barricading. Also, another illustration or another table, the building in danger of collapse. The building is danger from collapse of adjacent structure. Maybe the structure itself is good, but the building next to it is in bad shape and there is a chance that it might collapse. So in this case, we are going to put unsafe for all these scenarios. That building is in danger from geotechnical hazard, slope failure. Maybe the building itself is okay, but the foundation is really bad, especially those are the slope. Okay, building structurally safe, but other hazards like rupture gas, toxic chemical spills prevented from use. So probably the gas or the pipe, the gas line has been broken and we have a fire. So even the building, it seems to be okay, but the presence of any of these conditions will make it unsafe. And the same story, limited entry and so on. So here buildings, here are the equipment and falling or other hazardous material. So I know there is a lot of reading in these two chapters, chapter 15 and chapter 16, not too many calculations, but it is just reading and reading and reading. And the summary I provided in chapter 15 and 16, based on what I heard from the engineers that they used my books before, they are saying that it was sufficient or help them to pass. Let me put it that way. But I still believe that you need to secure these two documents, ATC 20 and ATC 20-1. The following pages are some examples that are taken from the ATC-20. And I put it by material as they put it in chapters. Wood frame structures, and what I did, I put it in a form of a table. So this table I generated based on the discussion and description in this chapter. I believe this was chapter 6, if I remember, of the wood frame, the one I just showed to you. Here it is, chapter 6, an inspection of wood frame structures. So I read and I did my best and I tried to do whatever I believe it is presenting the location and the type of failure and the failure or damage characteristics. So if you look to this picture, which is taken from the ATC 20, this is the wood frame structure. And you can see here, this is the cribble wall I was talking about. The cribble wall, this is a short wall when the house is raised floor. So this wall here is a short wall. We call it a cribble wall or a cribble wall. And normally nobody goes under this or under this, under the house, and there is a lot of moisture or damage could happen. This is why we have to inspect it from time to time, and normally we strengthen this cribble wall or cribble walls by some kind of plywood or OSB. So we need to look to that. A sliding off the foundation. Maybe the house, this is a concrete slab, sorry, the footing, concrete footing, or it could be a slab, but normally footing, okay? It could be the house is not anchored, so I look for the separation here, okay? And they point out the most important areas based on their experience, the ETC20, based on their experience with these type of structures, and what was the most common failure area or the failure between members or between the foundation and the structure itself and so on. For example, they mentioned the chimney, collapse or crack the chimney. This is the chimney. Maybe the chimney is separated from the wall due to the earthquake movement. So a picture, it does have some illustrations to show you the failure or the damage that you should look for. And this table here, I'm providing, for example, a sliding of the foundation, lack of sill bolting, the sill plate, because if you remember, we have the foundation, the footing, and we put the sill plate, and we anchor the sill plate with and the foundation like this. And we talked about this in chapter, by the way, the geotechnical chapter, chapter 11. Yeah, chapter 11. So if we don't anchor, this is a sill plate, and after that, the studs will come on top of the sill plate. The vertical, remember the studs? So this is a sill plate. So if the sill plate is not anchored well to the foundation, the house may slide. Okay? And I believe in the PowerPoint presentation, I sent also, by the way, in the USB. I don't know if you get a chance to look at it or not. In the USB that we send you, it does have the PowerPoint presentation, 3 presentations. If I do have them also, and I remember I sent them before, but I will be glad to send them again if you feel that you would like to look to them again or you don't have access to it. So these PowerPoint presentations, they have a very good illustrations, and one of them is showing the house has been moved completely out of the foundation, slides off completely. So what might cause this? Inadequate anchorage or of the sill plate to foundation. Shear failure will cause the anchor to be sheared or bent. A cribble wall failure, which is the weak story irregularity. If you remember the irregularities, the type of irregularities, the vertical and horizontal irregularities that we discussed. So this is the cribble wall here. This is the short wall of the raised foundation type building. So inadequate or lack strength of the shear walls due to cribble wall location. Large openings for garages or parking. This is a picture I was showing you. When they have large area, this is going to create a very weak, okay, story. Here it is. You see, this is the opening, and this is the parking here. You will find that this is a serious issue. And the same story here, you see, because of the earthquake event. So these walls are not capable of supporting the structure above, and it did fail. And this is why they did a lot of retrofit for these types of buildings in the San Francisco area and south in San Diego and so on. they strengthen this retrofit because it is a source for damage or a source for failure. So what I need from you, I will go over these examples, but when you are preparing yourself, for example, a chimney, what should you look? Inadequate anchorage, okay, to the roof or the lack of reinforcement and so on. So it may be separation between the chimney and the walls. We need to look for that to see if there is any separation has been occurred or not. So this is um, a discussion that, or the summary here is extracted from the chapter, the appropriate chapter, chapter 6, for example. Again, for the materials like concrete frame structures, illustration, and this is their drawing, by the way, not my drawing, and they are talking about failure of concrete frame structures, figure 15-11. They are showing here concrete frame, beams and columns, and we have the slabs after that. A frame is beams and columns, and after that the slab will. So if you look to any time you see that it cracks at almost 45 degrees, this is a shear type crack, by the way. This is a shear type crack, shear. Due to the maximum shear is 45 degrees, almost 45 degrees. So they are looking or identifying, for example, here. This is the masonry that has been filling this. You will find that the crack may be the diaphragm, which is the roof in this case. It has some damage or distress. These materials here, by the way, or these precast elements, we call them cladding. This cladding will come and they precast, and after they construct the beams and columns and or construct the frame, they are going to come and they attach this cladding to the beams. So damage a cladding connection. So these materials, the precast material, this is a serious issue, and it could cause a lot of damage or a lot of injuries, or even sometimes cause death, because they are not attached very well. So the cladding materials like this, we need to look to that. If there is any column out of plumb, the column has been considered to be perfectly vertical, it may be a little bit off. So we look to that. And again, I provide you with a table to see what type of failure, column compression type failure, cladding damage, and so on. The beam column joint X cracking, which is a shear stress cracking. Here it is shear strength. Okay. So if you go to the second type of material or construction structure, is a flat slab. Slabs, as you know, one-way slab or two-way slab, this is a flat slab. A solid flat slab, as you can see here. And these are the columns are supporting the flat slab. They found that we have something called bunching shear. This is a bunching shear. Okay. The column will penetrate through the slab. This is a slab. And this is a serious issue, which is the bunching shear. It is bunching shear type failure. flat slab floor system without a drop panel or column capitals. In order to minimize this type of failure, and I believe I have a question also in the 626, and I do have a drawing showing how can we improve or minimize the effect of the bunching shear, is to increase the area of contact between the slab and the column. And I believe in the question, so let me draw it for you, and after that you will. So this is the flat slab situation where the bunching shear will be a problem. Because if you look to the shear diagram, by the way, the shear diagram is going to be like this. So the shear at the center of this column is maximum. This is V, the shear force, V. So this will force this column to bunch through the slab. This is the slab, and this is the column. So it will bunch and it will go through as illustrated here into this diagram. In order to minimize the bunching shear, minimize or eliminate it, we can increase this area here. How? Like this. And they probably saw it. They provide a capital like this. This is a column. It could be done this way, or it could be done this way, steps, in order to increase the area so the shear will be smaller. You see this here increasing the area. And you notice this, by the way, for bridges. When they do bridges, you'll find that the contact between the column and the superstructure is like this. Okay, we don't have a 90 degrees, we make it okay parabolic like this in order to increase this here, in order to have a larger area. So the load that's coming from the column will not bunch through the substructure, the superstructure, sorry. So in order to increase, and I believe I do have a drawing. Those of you who get a chance to look to this question in chapter, not in chapter, sorry, sorry, I have, I believe in the solution. I illustrate this in the solution. I don't know which problem is that. Probably some of you already much faster than me locating the this illustration. I will spend 22 seconds. If I'm able to find it, that's good. If not, I will locate it. And I believe I draw something similar to what I just draw in order to illustrate to you the bunching shear, or how can we eliminate the bunching shear or reduce the bunching shear. Or it may be, you know what, it could be at the end of this chapter. I will look, if I'm not located in the 606 to 6, so probably I will locate them in the, unless one of you maybe say, oh, here it is. And I used to memorize these things one by one, but over time it seems to me that I start to forget let me, I think it is in the book maybe. Yeah. And we'll see it. We'll see it. I will show it to you, and I'm sure that um, um, not here, not here. Okay, that's fine. It's drawn somewhere. So this is the bunching shear. So I need to be familiar with this bunching shear. So the following is a different type of structure material is steel frame structures. Also the picture and the location and the type of failure. So, and so on. So I needed to be aware of these precast concrete structures. Also the precast, the one, as you know, concrete structures could be either cast in place or a precast. A precast, this is where the precast, the material, the beams and the columns and they bring it, okay, precast. And the concrete followed by concrete shear walls. And the shear walls, okay, we are looking for the cracks at the corners of the openings, corner cracking at the openings, something very, very important. And the shear in the piers, do you remember what's the definition of a pier? Piers and beams. So these cracks, these diagonal cracks here, this is a shear type crack. So, and I explained here, it is a shear failure, a cladding damage. The cladding, this is the exterior or corner cracking at the opening. Or it could be a diaphragm distress. The following one is a tilt-up structures. This is where they bring these members and they assemble them in the field, basically walls, concrete walls, and they assemble them in the field. And normally we look for the out-of-plane failure, wall panel separation, because the anchorage between the walls and the roof is North Ridge earthquake was a good example for that, where a lot of structures failed due to this inadequate anchorage between the walls and the roof. Okay, because they are not cast in place, they are precast and they bring them. So the tilt-up structures are subject to separation at the walls, roof. So we need to be aware of that. Also, the shear cracks at the corner, we need to pay attention to that to see a separation between the diaphragm. Okay. So the URM, unreinforced masonry structures, those are the masonry is a brittle material, as you know. So shear is going to be a serious issue. Shear cracks. And here are this is unreinforced masonry structures, which if you remember in chapter 2, I talked about the URM. And I need you to be familiar with the URM in chapter 2. Let me remind you, chapter 2. Let me, chapter 2 of my book. Here it is. URM on page 187. Sorry, page 87 only. Unreinforced masonry building, URM, because masonries, okay, or masonry structure, they are cementitious materials and they are very weak in tension and strong in compression, yes. And I need you to be familiar with the URM because after 1933 earthquake, by the way, which is the Long Beach, it was a serious earthquake, Long Beach earthquake in 1933. They have a Senate bill that require that all seismic retrofitting of the existing, and I talked about that in chapter 2. I needed to review this again. This is on page 87, please. Look at it because the URM, it could be a subject for a question on the exam. Unreinforced masonry and for the tall building, this is the URM, by the way, short buildings, low-rise buildings. And for the URM, tall buildings, also these old tall buildings that made of masonry blocks, also the type of failure and the X cracking, the shear cracking between the openings, which is piers, and so on. Shear cracking like this one here, spalling, diaphragm damage or distress. So those are examples that I extracted from the ATC 20. The following section is seismic retrofit of existing structures. So after 1971 earthquake, they found the structure engineers or the local, after 1971 earthquake, they start to look to the buildings that constructed before this, and they said that we need to strengthen these existing structures if they are not meeting the code requirement or requirements. So what is a seismic retrofit by definition? A seismic retrofit is defined as modification of existing structures to make them more resistant to seismic activity, ground motion, or soil failure due to an earthquake. This definition I need you to be familiar with what is meant by seismic retrofit in general. If you are doing this retrofit to a structure or you are doing this retrofit to a bridge, okay? It's basically you take the existing structure and you try to modify it. Why you modify it? To make it more resistance or provide more resistance to seismic activities and motion and so on. It is important to keep in mind that there is no such thing is called earthquake-proof structure. There is no such 100%. No, there will be some damage, but we need to minimize the damage. We don't need structure failure. Okay, and this was discussed also in chapter 6. So, what are the levels of modification? What kind of modification you are doing for an existing structure in order to retrofit? So, here are different types of modifications. And it depends how much money you are willing to spend. Seismic retrofit is primarily applied to achieve public safety with various levels of structure and materials survivability determined by economic consideration. Because how much money you are willing to spend to make this structure more resistant to seismic forces. So, for example, public safety only, structure survivability, the primary structure and damage, and the structure unaffected. And I discussed these items one by one and in very brief. And I start to talk about some types of modifications. Hybrid solution, where you put some kind of materials together Base isolators, very, very common. Base isolation is a collection of structure element for a building that should be substantially decouple the building structures from shaking ground and so on. Like, so base isolation, they are using this a lot. Dampers, like the one they use it for rockets. Dampers, like in your car, shock absorption, Damper absorb the energy. So dampers for tanks, slush tanks. Another way of providing strength is shock absorber. Tuned mass dampers, and each one has advantage and disadvantage. It depends on the cost, and I briefly discuss each one of them. You need to know just only the name, just to get an idea. Okay. Active damping with fallback, this for skyscrapers. Sometimes we provide reinforcement. Okay. Extra reinforcement. Connection between buildings and the other expansion additions. And I gave you some examples. I know the pictures in the original book is your book much better. I made a copy today, but I believe the original picture is much better. Okay. This figure 18. Okay. So please look to these things, and there is a picture here already. I talked about it before, which is related to seismic retrofit of concrete bridges. And this picture is taken after Northridge earthquake. The reason I'm looking back, because I found that this picture here is figure -22. I'm referring this as a figure dash, showing figure the exterior shear reinforcement. But even the order of the picture I'm looking to see in my original book here, it seems to me I took some pictures from the previous book, because this is figure 5:15:17 here. And I will look to this one more time. This is a 15:18, figure 15:18. I wonder why this is 15. So this is supposed to be 15:19, and this is supposed to be 19, supposed to be 20, unless I'm missing something. I'm looking here. No, I'm not missing anything, but it could be a typo. So this is 20, and this is 21. At least I can make an errata of that. 21, and this is 22. So probably the figure numbers, or the numbers has been, it's just something that caught my eyes right now. So I apologize for that, but there's a minor thing that. The picture on your book, by the way, is much better than this copy here with the copy machine for some reason. This is how it looks like, which is infill shear trusses, where we add trusses outside the structure itself in order to increase the strength of the existing building. this picture here, the one shown, this is Northridge earthquake column failure. And I believe there is another column here, which is this picture here, the following page. This type of the column that we said that we don't like to have in any earthquake area or earthquake activity area, because this type of the column is a tight column. If you remember the types of columns, we have tight columns and spiral columns. And the tight columns, these are, so the columns, either for bridges or for structures in general, it could be either tight columns or spiral columns. This is a desirable one because the tight columns, what you'll find the vertical reinforcement, and we put a tie to hold these in place. A tie, and the tie spacing between ties, this is a tie, normally number 3 or number 4, a tie, but these vertical bars are the one is carrying the axial compression for columns. They found that these ties, the concrete between the ties, it will be damaged as shown in the picture. For the spiral column, they said, no, we're not going to put ties. We're going to keep the vertical reinforcement as shown like here, but we are going to put a spiral, a continuous loop around this. So when they test these columns, the tied and the spiral, they found something amazing, and I showed this picture a couple times before, by the way, or this graph. If this is a B delta curve, you will find that for a tight column, it will go all the way up to here and it will fail. This is a tight column. But if you look to the other one, the other column, and let me use different color. The spiral column, it will follow the same load carrying capacity like this one here, but it will go all the way up to here. This is the spiral one. Why the spiral is better than the tight? Because of the total energy or the toughness. If you remember what's toughness, toughness is the area under the stress strain curve or the load deflection curve. So spiral columns are tougher. And at the beginning of chapter 12 or chapter 13, when I talked about concrete, let me show it to you one more time. Yeah, under chapter 12, that's correct. Here it is. This is the figure I'm referring to, figure 12-2. This is a tight column, and this is a spiral column. And this is the load deflection curve, B delta curve. So as you can see, the tight column, it goes all the way up to here, meaning that the energy that can be absorbed by such column is much higher than the energy that absorbed by the column, the tight column. So, and this is why you'll find most of the column that we do it here in California, we are using, if not all right now, all of them, we are using the spiral, or is a continuous loop, because this continuous loop here, what is the advantage of that? This continuous loop or spiral, as we call it, spiral. This is providing what is known as a confinement, lateral confinement. This term is very important. Lateral confinement. Lateral support. And this lateral confinement is going to increase that the energy that can be absorbed. So, and this is what for the seismic retrofit program that started after, as I told you, the San Fernando earthquake in 1971. This was a major earthquake in 1971. San Fernando earthquake opens the eyes of the structural engineers to look to the bridges and look to the buildings in general. But the bridges, it does have a special program, seismic retrofit, where they increase the capacity of the substructure and the superstructure by strengthening them. And when the earthquake, 1989 Loma Prieta earthquake, and after that Northridge earthquake, all these earthquakes, by the way, taught us or taught the engineers or the structural engineers or the code writers a lot about the failure, and the retrofit program was based on the evaluation of these structures after they subject to this. Okay, so I needed to read that seismic retrofit for bridges, and I provided a picture, by the way, if you go to the text and in chapter at the beginning of the book, I provide a summary. And this summary, for example, on page 50, you'll find a picture of the seismic retrofit program. The seismic retrofit, retrofitting freeway structure, what they do exactly. They are providing, for example, for the columns, they provide a steel jacket around it. They started, by the way, with some composite materials, but after that, they start to use a steel jacket. So this steel jacket is providing lateral support or lateral confinement for the columns. Okay, so basically, if you do have an existing column and they need to strengthen this column, so they provide a steel jacket, okay, two steel half circles, okay, and they close it, so semicircle, and they close it, so steel jacket around the column, and also the footings and superstructure. So this picture here shows the seismic retrofit of the freeway structures, what they do for the, and the connection between the substructure and the superstructure or the columns. The footing, also they increase the strength of the footing by additional piling and additional lateral reinforcement or reinforcement. So all this I needed to be aware of. Okay, so this is chapter 15. I know I talked a lot, but there is no discussion or there is no, calculations, but we need to be ready for these type of questions because they might ask you. The sample problems I have at the end of chapter 15, problem 15-1, seismic retrofit of duct and piping primarily consist of which of the following measures? You have duct pipes, okay, duct work, okay, any kind of duct work like AC ducts and so on, and piping in general. Provide lateral oscillation brace, provide longitudinal, provide either lateral longitudinal or seismic bracing is not required. No, there is required. Seismic bracing is required. So this is out. Okay. If you look to the any pipe, like any kind of duct or piping, you will find that this is called longitudinal direction, and the one perpendicular to it's called lateral direction. Lateral. So when we have an earthquake, the pipe starts to swing back and forth this way. So we need to provide the lateral oscillation. We need to provide the pipe from oscillating laterally. So we put some kind of support like this. Okay. And there was a problem, by the way, in chapter 7. You remember the problem in chapter 7 was solved here, which is the force in the lateral place. Lateral place. Okay, let me bring the picture and you will see, yes, we did it. Here it is. Do you remember this problem 711? 711. This is exactly what we do. If this is a pipe, in order to prevent pipe from oscillating back and forth, we provide a lateral support like this. Attach it to the roof and attach it here to the collar around the pipe. So when the earthquake is happening, the pipe, because the pipe is supported by these hangers, if there is nothing to prevent this from oscillating, this is going to be a serious problem. So we do the same thing. This is a pipe or a duct. So going back to chapter 15, you will find that the answer A, which is provide lateral oscillating braces, is the correct answer. Okay, so we select the answer A. And here it is. If you know the difference between longitudinal direction and the lateral direction, this is the answer. If you look to the following question 15-2, the shear cracking in piers or in the piers, X cracking, shown on the figure to the right are caused by which of the following loading? These X cracks out of plane on a plane masonry shear wall, in plane loading on a reinforced masonry wall, out of plane loading on unreinforced masonry wall, or in plane loading of unreinforced masonry wall. So we have a wall like this. First of all, if this wall is reinforced, so if this is a reinforced masonry wall, this one here, and this one here, if they are reinforced, those two answers are out. Because reinforcement will intercept the cracks. I needed to be aware of that. So the reinforcement will provide horizontal, as I remember, and vertical reinforcement. And I talked about this in the masonry section. So the vertical reinforcement and the horizontal reinforcement, because we have a code, we have vertical reinforcement. And do you remember the vertical and the horizontal reinforcement are required? These reinforcements will intercept the cracks like this one here. So if it is reinforced, the cracking will not show up. And when we're talking about that the wall is reinforced, mean that reinforced with the proper amount of reinforcement per the code. Okay, not any amount of reinforcement. No, the reinforcement, it should be according to the code, the current code. So if you put the proper amount of reinforcement, the horizontal and vertical, per chapter 13, if you go to chapter 13 of the masonry, you will find that. So these two answers, I needed to remember the process of elimination. The process of elimination, the one I talked about it, and I mentioned in every class I'm teaching. The process of elimination. Get rid of the answers that so I'm still between 1 and 4. What is out of plane? Out of plane is a perpendicular force. If you remember out of plane force, so if you look to any wall, there are two, and we talked about this, and we solve problems, by the way, out of plane force. And there are some equations. So if you look to the wall I'm talking about here, out of plane means that the force is perpendicular to the wall. This is called out of plane. Out of plane. This is almost perpendicular. In plane means that in the direction. This is in plane. Or I can draw it here. This is in plane. So these cracks that indicated to be like this is going to be caused by this or this. First of all, it is unreinforced masonry wall. And this is the answer 1 and 4. Both of them unplane or unreinforced. Plane means unreinforced. Here he called it a plane, and here it's called unreinforced. So obviously, this is the correct answer. The in plane, and this is what the answer 4 or D, and here it is. I know the naming is very important, or the terminology they are using. This is the figure I'm referring to. Out of plane means perpendicular. Here it is. In plane means parallel. I drew it for you already. But again, see figure below this figure here and figure 16-5. Figure 16-5. In chapter 16, I don't have, unless I'm referring to another figure, I don't have figures, figure 16-5. No, I believe I need to look to that. Seems to me the figure here is, because this figure here, I'm sure that I'm referring to, I will show it is in figure 13-5, if I'm not mistaken. Let me see. Yeah. Because it could be a typo. Yeah, here it is. Yeah. Figure, this way I said figure 13-5. It's correct. Is a masonry section talking about the cracks. So again, this figure 13-5. Okay? Because it does not make sense. that I'm referring to figure 16-5 because chapter 16, since I'm the one who wrote these things, so we're referring to this figure is taken from, okay, this is portion of the figure 16-5, by the way. So if you'd like to even see the figure, see the figure, okay, or attached figure. But if you'd like to go back again to figure 13-5, it has the same, but it does have the other cases. But this is a case that we are interested in. Make sense? So the following problem: after an earthquake, who can perform building safety evaluations and damage inspections if requested by the local building officials? A qualified building inspector? Yes. Any inspectors? Civil engineers? Yes. Structural engineers? Yes. So all of them. So the answer is D. Okay, and the building inspectors qualified mean that he got the proper training and he has some kind of certification, and probably some of you already have this certification. I know a couple friends, they have it. They attend the course and they show them how to. Problem number 15.4, structural system failures could cause or could be caused by bending or flexural stress, shear or tension, or compression, or a combination of them. Which of the following failure modes might cause a structural collapse? Structural collapse is a serious issue. We don't need the structure to collapse. Yes, we know or we are expecting the structure will suffer some damage, but we don't like the building to collapse completely because this is a serious issue. Shear in a slab, concrete slab, or shear in a column of masonry, or flexure cracking in ordinary reinforced masonry shear wall, or tension cracking in a diaphragm cord. If you look to columns, columns are critical members. Columns are critical members in any structure. And when we are talking about shear in column, mean that the column will be sheared like this. It could be so when you have a column that is sheared like this, the entire structure will collapse. And this is why we selected the answer C, which is in the reference to the shear that might occur in columns. Bunching shear, the bunching shear is a serious issue. And we explain what bunching shear is. And I'm still looking for the picture, the one I told you it might be a very good illustration for the, which I draw it for you, but if I remember correctly, I draw it somewhere here. And I'm trying to do it, to locate it one more time if I can, very quick. If not, I will try to locate it. I remember in this book, if I'm not mistaken, and unless by mistake is not here, or probably I mix. But if I remember, I saw it. Okay, I'm getting close to see what. No, it seems to me that maybe in the body of the problem itself, or I draw it in the question itself. I'm looking for the answers, but probably in the body. showing these different types of configuration for bunching shear. Yeah, okay, that's fine. We talked about the bunching shear failure is most likely to occur in which type of the following structures? Flat slab concrete structure, yes. Reinforced masonry, tilt up, unreinforced. So the flat slab configuration, a flat slab. And this is a column and the bunching shear. And I remember I sent you a picture of a bunching shear, by the way, from a structure analysis book I used when I was teaching structure analysis. This book here, structure analysis book, one of the books I used when I was teaching structure analysis. If I remember, I took a picture from here and I sent it to you. It does have a very interesting picture of a bunching shear for a bridge. Let me see if in this book or yeah, I remember it was here. This is wind. Do you remember this bridge here? The Tacoma Narrow Bridge, the wind. And where is the seismic? Probably in another book. No, here it is. Here it is. You see this column here? You see these columns, they penetrated through the slab, this bunching shear. So this is the slab, and the columns penetrated into the, you see that went through. This is a very good example of a bunching shear instead of the illustration. And I believe I made a copy of this. I can make a copy again. Let me put a tab here. At least I can send you this, an example of a bunching shear. Um, um, okay. So, and in order to eliminate or minimize the effect of the bunching shear, as I told you that we do this drop panel like this, or capital, or enlarged area, or drop panel like this, step panel like this. In order to increase, because the shear concentration is here, so if the shear is acting over a larger area, the shear stress will be less. Okay, so this is, I have some additional questions here, supplemental question for chapter 15, 15, 6, 7, 8. These things are really, really good. And I provide you with the answers. So here are the answers for these additional supplemental practice problems. And all these problems, by the way, they are included in the 6 to 6. I said I collected all the problems I have and I put them in this. Okay, we'll take a short break and come back to talk about chapter 16. Chapter 16, which is the last chapter of my book. And this is another chapter also does have a lot of talking. A lot of talking. So let's take a few minutes break, 10 minutes or so. Right now it's 3:25. So 3:35. Come back with open mind and open heart. Get some fresh air and come back, please. Thank you. Okay, chapter 16, which is the last chapter of my textbook. The title is Structural Tests and Inspections. And this chapter, chapter 16, is based on chapter 17 of either document, either IBC or CBC. But as you know, CBC, California Building Code, they have the A chapters. We need only chapter 17, not 17A. If you have the IBC, it is chapter 17, because CBC does not have, IBC does not have the A chapters. So I need chapter 17, okay, from either one. And I highly recommend you to have this chapter, the entire chapter. What I did here, I did summarize or provide a summary of this chapter. But as I said, that get the entire chapter, and I recommend you to read it 2 or 3 times, as if you are reading the first time a paper, a newspaper, and you will grab some concept, and after that read it again. In the past, by the way, in the previous codes way back in 2000, this chapter used to be only 2 pages, 2 or 3 pages, if I remember correctly. Very short. But you will find this chapter became a little bit thicker and healthy. Because of what? Because of the tests and inspections that we do in the field. They found that the lack of testing and the lack of inspection in the field can cause a lot of damage for structures or structure damage. So as you know, we design, we analyze, analysis. We have a building, you analyze it using whatever software or do it by hand, whatever analysis, to get the shear force and the moment and the normal force. After you analyze for whatever loading, because you know the structure will be used as a hospital or a library, whatever the function or the functions of the structure. After you do the analysis, and nowadays we are using computers to do all this analysis for us, we'll go to another phase, which is design. You design the structure, you design the foundation or foundations, what type of foundations, and beams and columns and connections and all this fancy stuff in the design. So you design the structure after you are using the, or after getting the moment and shear and normal forces. This is a design. You prepare a set of plans and you advertise it, and it will go where after that? It will go to construction. Where you are bidding on the job, and the contractor will come and build your facility as you design it or as you provide. During construction, if the foundations are not inspected well, there will be deficiency. If the slabs are not inspected well, will be deficiency. If the columns, and name it, if the connections. So the entire chapter here is telling us, in order to ensure that the building will be constructed as designed, if there is a welding, I have 2 members to be welded. How I know that the welding is done correctly? If I'm using bolts, I'm connecting two members using bolts. Did the proper tension to the bolts or not? And so on, name it. Every single material or every single connection, it does have specifications. Welding, how thick is the weld is, what type of weld. So the purpose of this chapter is to verify the testing and the inspection in order to ensure that this building is constructed according to the design and follow everything in the design in order to, if you have an earthquake, the structure will not fail. Because they found, for example, in Northridge earthquake and Loma Prieta earthquake also, they found that there are some welding members, they failed because the welding was not done according to the specifications or according to the design. So a lack of an inspection and lack of testing could really lead to failure. And this is, you can say, this is a summary of the whole chapter. Okay. So what I did, here are the topics that I include in this chapter. There are two types of inspections. We have something that's called general inspections and special inspections. And I start talk about each one of them. And the statement of special inspections and special inspection for seismic resisting. This is very important. This is one of the important topics in this chapter. And finally, structure observation is the second important topic. Everything is important, but I'm telling you that there are some items. You will find this chapter, by the way, chapter 17 of the IBC or CBC, full of tables. And these tables, they identify the operations or the tasks that it needs continuous inspection or intermittent or periodic inspection. For example, just I opened the chapter. If you go to page, for example, page 489, for example, you will find these tables. These are taken from chapter 17. We have what is known as a continuous special inspection. Continuous means that somebody has to be there during, from the beginning to the end of the operation. For example, here, this is the required special inspection and test for soils. And they have for concrete and for timber and for steel, every activity. For example, here, this one is continuous. Why this is continuous? What activity is that? Verify use of a proper material, densities, lift, thickness during placement and compaction of compacted fill. The inspector must be there. Okay. Okay. And this is specific item, for example, item number 4, just as an example for the, when we build roadways or streets or highways, any embankment, it is this is an embankment, for example, or fill. We call it fill or embankment. And this is the original ground, OG, as you know. And we call this point is a catch point, CP. Catch point, CP. And this is also CP. By the way, since I mentioned this, I just remember, I finished the surveying class yesterday. It was the second quarter. I used my new books, the second edition of the surveying books. And I finished the course yesterday. However, I added 2 additional sessions in order to help those who are taking the class, because some of them are taking the exam by the end of this month and the early July. So I added 2 additional sessions, by the way, which is next Saturday, which is 6/13, I believe, June 13, and June 20th. I added 2 additional sessions. Each session is 3 hours. I will send an email to you. I believe I sent an email. I don't know if you received it or not. If not, I will include it in the email that I will send it to you. These are free. I made these 2 sessions for free because during this pandemic, a lot of people are not okay. They didn't get a chance to take a course for whatever reason, financial reason or anything. So if I can help, I will not hesitate to help. So I made these 6 hours for free, which is almost like 1/3 of other courses available in the market. So to make it available for everybody, so it has only one ID. I was hoping to use the same ID of the course itself, but unfortunately, I thought that I did this yesterday. I told my class yesterday, but today I discovered that probably I did reserve it, but I didn't save it. Probably I was in a hurry. Maybe I did not push the button for save, so I lost the ID. So it came with an ID, but anyhow, it will take about 2 minutes to enroll. So if you would like to attend in these 2 days, you will get the hours. I believe 1 in the morning, 1 in the afternoon, if I remember correctly, from 9 to 12, and from 1 to 4 here, something like that. I can remember. So, but you will get it. You will get, if you are interested to attend this surveying review for free, 6 hours, you will not lose anything if you are interested. If you have a friend or a coworker or even your kids can attend for free also. So you can bring the kids and tell kids, okay, prepare yourself for the surveying exam that you are going to take later on. No problem. So as I just remember, so going back to the fill or the embankment, when we build this embankment, we build it in lifts, a lift, okay? Each one is 6 to 8 inches, sometimes go to 10 inches. So each lift, LIFT, is about 6 to 8 inches or 10 inches, as I said, depends on the type of the soil. This is a lift. So after we put the first lift and we compact the soil, we put the proper water, we need to inspect to see if somebody has to be there during this operation. The contractor is working and the inspector must be there. This is what is meant by continuous special inspection. And he must be certified inspector to inspect. He must have a certification. But if you look to the second column, you will find that it's periodic special inspection. Periodic mean that he can go and do things and leave. For example, verify materials below shallow foundations are adequate to achieve the desired or the design bearing capacity. I need to go and check it and leave, and so on. So you will find that this is the theme of this chapter, that they have 2 columns, one for continuous and one for periodic. And they list which type of what task requires continuous and what task require periodic or intermittent. So I need you to be aware of that. This is something very important. And so the chapter started by chapter 16, started with some basic definitions as listed in the code, either IBC or CBC, as I mentioned. What is the scope of this chapter? What's the purpose? This scope means what we're trying to. The provisions of this chapter shall govern the quality, workmanship requirements, for materials covered, materials for construction and test shall conform to the applicable standard listed in this code. So we're testing materials, okay, that we are using. And here are the definitions. I provide you with the actual language given in the code. You are very welcome to read them. But for example, what is meant by special inspection? This, we need to know that. And the structure observation. We need to know these two definitions because they might ask you about that. For example, special inspection of construction requiring the expertise of an approved special inspector in order to ensure compliance with this code and the approved construction document. So somebody must have the expertise to do that. Somebody who knows welding. I cannot get anybody to check the welding to see if this welding is done correctly or not. Does this welding meet the specs or not? Somebody must be certified for welding, okay, and so on. And there is a certification program. I participate in this, the ACI certification, the American College Institute ACI certification. I participated a lot in this by giving lectures and led the inspectors to do testing, the cylinder, the sieve analysis, the slump test, the air content of concrete, and so on, using the pressure method or volumetric method. All these tests that you've done, so they have to follow the certification has two parts, the writing one and the practical one, or the so the same story with the welding and so on. And you know, there is a testing for everything nowadays. And so this is why for the PE you have to take all these exams in order to be a registered PE. So continuous special inspection, the one I was talking about. What's continuous? That special inspection by the special inspector who is present when and where the work to be inspected before. He always there. But the periodic one, the special inspection by the special inspector who is intermittently, here it is, the word intermittent. He not necessarily to be over there at the job site all the time. He will go to test whatever he's supposed to test and leave. And based on the tables listed in this chapter, they identify for us which one is considered continuous and which one is considered periodic or intermittent. So in present, where the work is expected, and so on. Structural observation. This is the second important definition or term I needed to be aware of it. Structural observation. The visual observation of the structure system by a registered design professional for general conformance to be approved the construction document, significant construction stages, and at the completion of the structure system. A definition, and nobody will ask you to memorize it, but we need to know what is meant. And if you are asked a question related to structural observation, which you are going to see it again, you should be able to come and compare. So here it is. I went over and I summarized this chapter 17. It was very tough task for me, because how to summarize a chapter, especially talking. There is no any calculations like chapter 15. There was no any calculations or equations or anything like that. So it is a very dry subject, and I encourage you to read it more than once. So please do your best. I did all my best, and I provide some tables for you, not necessarily to be their tables. This is my tables. For example, what's the difference between what is attesting, for example? What's the definition attesting? What is approved agency? Okay. For example, approved agency, an approved agency shall provide all information as necessary for building official to determine the agency meet the applicable requirements specified in section so and so and so. Testing, what is attesting is? Okay. And in fact, by the way, when I was teaching the class, the testing, there is a huge difference between a test and an experiment. Normally I discuss this the first day. What is the difference between test and experiment? A test is a set of steps to be performed according to certain specifications, and normally we use ASTM or AASHTO. In a testing, it should be done according to ASTM or AASHTO, the American Society for Testing and Materials, or the American Association of State Highway. So testing, and the outcome from a test is known in advance, or at least the boundaries, the limits, the upper and lower limit. This is called a test. But when you do an experiment, the most important difference between an experiment and a test, the outcome from this experiment is not known, unknown, but the outcome here is known. When I determine them, when I test a piece of steel to determine the modulus of elasticity for steel, I have a specimen and I do testing according to the ASTME8, by the way, and I do the testing and I determine the modulus of elasticity of this material. I know the outcome, I know the limits, I know what's the minimum and the maximum, so I know the results in advance. Okay, or if it's not exact, I know the limits, the upper limit and the lower limit, the boundaries. But the outcome from an experiment is not known. If you ask me what is the relationship between, for example, imported banana and coronavirus, I don't know. Just sorry for using this. Oh my God, COVID-19. I don't know. Do we have any relationship between the imported banana and the COVID virus or COVID-19? I don't know. Just I'm using this just. Or what is the imported banana and the allergy? Or what is the relationship between the imported banana and cancer and whatever is? I will not know until somebody will come up with how many tons of banana imported this year and how many COVID-19 cases we found in this month or this year. If there is any relationship, maybe you can come up with a relationship. Okay. So maybe, so the outcome is not known to me. I don't know what will be the outcome. Just to show you the difference, I'm using very extreme example. God forbid there is no any correlation between banana because I eat banana and any COVID-19 because I get banana yesterday, by the way. So just don't worry, eat banana, don't worry. Okay, there is no any correlation between banana and or imported banana and COVID-19. Okay, just I'm using. Okay, so there is a huge difference between the testing, a test and an experiment. So let us go over this very quick. Type of inspections, we have what's known as the general inspection and the special inspections. The general, this should be performed for construction work when the permit is required. But the special, right now for the materials, installation, fabrication, and so on, and somebody who is expertise in this field to do that. We have something called the preliminary inspection and final inspection. And I give you the sections, by the way, from IBC if you'd like to And I start to talk about general inspections. Again, this is like a brief summary of what is in the code, or maybe sometimes I stick with the language because the language is very, very important. So please read this because the reading is not really difficult for you. I know you can read very well, but I will highlight what I believe that you need to know, especially in inspection. Yes, we need to pay attention to that. Okay, special inspection. And we have something is called uh, the statement of a special inspection. What should be included in the statement? Here it is, like the report, if you like to look. The special statement of a special should identify the following. I needed to be aware of that. Here it is, seismic requirements in a statement. Okay, in the statement, it must be also this, should be paying attention to this paragraph here, and also there is another paragraph is coming. So the tables, as I told you, structure observations. What is the definition of structure observation? And here we start to look for a structure observation for structures like risk category 4. Do you remember risk category RC4? Okay. So anything related to seismic, I will structure observations for seismic resistance. So this, I would say yes. Pay attention to this. That structural observation shall be provided for those structures where one or more of the following conditions exist. Is the structure is classified as risk category 4, RC4. Do you remember RC4? These are the essential facilities. Do you remember the table shown in chapter 6 for risk category 4? Let me remind you with this. I know you know it, but it will not hurt to. I know you memorize the book right now, and even you are faster than me right now. Can you go to page 204 of the textbook? Here is risk category 1, risk category 2, and RC3 and RC4. Those are essential facilities. Here it is. This is on page 204, please. And I told you use this table, don't use the table on the previous page. This is from the IBC, and I prefer the one from the IBC. If you go to the previous page, you'll find that when I was talking about this chapter, you will find that I say that there is a table also. It has the risk category, but from the ASCE 7-16. This is a table, okay, 1.5-1. They put the risk category to the right, but I prefer not to use this one. Not this one. I put it in order to tell you that not use or do not use. Okay, I prefer to use the other one because the other one is a governing one, and the other one is more detailed for the risk categories, risk category 1, 2, and 3, and 4. And you remember the risk category for the essential facilities, and we went over this, and you will see this in my discussion. Okay, so going back to the chapter 17, all the way to the end. So anything related to seismic, probably I will pay close attention, but I needed to read this summary first couple times, and after that get hold of chapter 17 and use chapter 17. Try to highlight as much as you can, because one question or two questions, they're worth a lot, and they could be a matter of passing or not passing. And I don't know, just for the sake of discussion, as I told you that we still have 2 sessions. I believe we still have 2. Yeah, we still have 2 sessions. We are meeting on the 21st, and we are meeting on the 28th. Anybody is taking the exam before these 2 dates? You don't have to tell me your name, but anybody is taking the exam in June? Let me put it that in general. Any of you is taking the exam in June? What about July? Any of you is taking the exam in July? Okay, July. So if you raise your hand, probably I will not call your name. Don't worry. June, okay. Okay, that's fine. It's just a matter of because the reason I'm asking is this is the second quarter, as you know. Here it is, second quarter. Okay, I'm working on the schedule for the third quarter, which will start July 1st. So July 1st, after the end of this quarter, July 1st will be something similar to this. It will be workshops, because you will get access also to the 55 hours of the on-demand with these 2 books, okay? And these will be like workshops like this, okay? But the reason that today I'm recording, always I'm recording, by the way, but today I'm covering chapter 15 and 16 because, as I mentioned at the beginning, for some reason the previous recording was corrupted for some reason, as I mentioned. So you will get, those of you who are enrolled in the class, you will get the third quarter schedule. Those who are attending the class with us, you are going to get the schedule, and those who are going to join us the first time, we will give them access to the on-demand, and also will give them, obviously, the access of the workshop, so they get both, as you are getting both right now. Okay, so going back to chapter 17, I am on page 487, please. Here we're talking about required special inspection. Also, differentiate between these two and give you some examples. For example, for concrete construction, and you'll see the tables on the following page. For concrete, periodic, verify use of required mix design. This is a periodic. I go and check, make sure that the aggregate, the coarse aggregate and the fine aggregate they are using and the mix plan are meeting the requirements, and leave. I don't have to be there during the mixing concrete itself, because I verify the ingredients, okay? But continuous, also for concrete operation, inspect of the concrete and the shotcrete placement for a proper application technique. I have to be there when they are pouring the concrete, when they are putting the concrete. I cannot go and sit in the car and go ahead and finish. No, I have to be next to the bumping truck, and at the top somebody is where they are placing the concrete. And I was doing this when I was the RE for many bridges here in California, in Fresno. Okay, so there is a continuous and there is a periodic. Who decided which task or which activity is periodic and which activity is continuous? The code, this code, chapter 17, based on these tables. If you flip the page, you will find, for example, a table for concrete construction. What is considered as a continuous and which one is considered periodic? And nobody will ask you to memorize. For example, this one here, it is a continuous. Which one is that? This is reinforcing bar welding. When I inspect a weld, if you look to the another X here, okay, inspection of concrete and the shotcrete placement for the proper application, the one I used it before. So you might be given one of these tasks on the exam, and they will ask you, do you consider, or there the code, which one is considered continuous and which one is considered periodic or intermittent? Make sense? Here's some additional, don't worry about it. This is standard from the ACI code, I doubt, or welding, AWS, American Welding Society, AWS, American Welding Society, ASTM, the one I was talking about, ASTM, the American Society for Testing and Materials. Nobody will ask you to know these codes here, because this is a huge different story. And the IBC reference, whatever the section is referring to. But I need you to be, and series of tables provided here, but I told you I did my best. I need you to get the original. Special inspection for seismic resistance. This is another section that also a lot of reading. Okay, I need you to read this. Okay, especially I need you to pay attention to the numbers. For example, here, special inspection for seismic resistance, and you will find that we have not exceeding 35 feet, where the SDS, the structure consists of light frame construction, design spectral response acceleration at short period does not exceed 0.5, and the building height. So probably it could be a target for a question. Okay, the same story here. So the key, the one, it does have numbers, limitations, height, or limitations on all these things. So I needed to be aware of that. Okay, so please read all these things, and another table here. And at the end, you can read all this, because I talked a lot about all these things. At the end here, I believe there is one thing that I needed to be aware of. It might be. Yeah, I will pay attention to the whole thing. I don't like to say, for example, they took the structure steel, and what are the seismic force resisting systems? What type of systems should, and if they mention the seismic design category D, E, and F, for example, those are the serious ones, as you know. So please read it, and the best way to do it, nobody will ask you to memorize it, because I don't memorize it myself, and read it, as I told you, 2 or 3 times, and you will get familiar with it. And this summary, I did my best, but I cannot guarantee that. This is why I encourage everybody to get chapter 17 of the IBC or CBC. So for example, here, per IBC 2018 or CBC 2019, chapter, who legally allows to employ one or more special inspector to provide an inspection during the construction of the project? Who has the authority legally? The word legal is very important. The registered designer professional, the owner of the project. What about the prime contractor and the subcontractor? Do you think that prime contractor and the subcontractor, if they hire an inspector, do you think it's a good idea or a bad idea? The prime or the sub? Do you think that the inspector will do a good job? And I provide an answer. Okay, so the answer is A, which is, in our case, the owner and the professional, the PE or designer professional. But the sub and the prime contractor obviously is bad idea. And here it is. I provide you with special inspection and tests. Who has the authority? And I provide you with the section. So this is a problem 16.1. The answer is A, which is the owner or the PE of this, because the contractor or the subcontractor, they have conflict of interest. The subcontractor and the prime contractor, they have conflict of interest when they have somebody who's doing the testing and then inspecting, and he made to be easy on them and so on. Okay, so I needed to be aware of that. So another 2 questions here. So please do your best and let me know if there is. So I know dry subjects, chapter 15 and chapter 16, but at least now I gave you or I clarify issues, and right now when you read it again you will find that it's not really difficult as you might think at the beginning. Make sense? Okay, so now I can open the floor for any questions. And as I told you before, if you are going to take the exam, and if we need any additional period, like for example the surveying, I did 2 additional meetings in order to help them, because they are taking the exam very soon. One is taking the exam the 22nd of this month, and I believe a few engineers taking the exam early July. So I added these 2 sessions. The one I mentioned, you are very welcome to attend next Saturday and the following Saturday. So we still have 2 meetings, the 21st and the 28th. We will solve problems. Give me exactly what you want me to cover from either 6 to 6 or from the textbook itself. If there is a topic or a subtopic is not clear to you or confusing and you want me to go over, I will be glad to do that. I'm willing to help as much as I can. But again, you need to sit and study. You need to sit and solve problems and challenge yourself. Without you challenging yourself, the passing will be a little bit tough, but I will do all my best. Any questions from any of you related to this book or the 6 to 6 or any other books? If you have any other books, if you are studying from other materials, I'm not against that. I respect every available material in the market. I'm familiar with all of them because I did my books way back, I believe before all of them, to the best of my recollection. But I respect everybody, and everybody is doing his best, and I'm doing my best too, and I really appreciate every effort by any other vendor to help you guys to pass the exam, because the ultimate goal is to pass the exam and get your PE and forget it, and no more CBT and no more seismic and no more. Okay, any question from any of you or related to any problem that you solve and you have difficulty understanding, and I hope that all of you tried the CBT and the CBT is working fine. The program is working fine, and if you have any difficulty or any technical difficulty or technical issue with it, let me know. I will be glad to get in touch with my programmer, and I will do my best to help. Okay, if not, so in this case, so I'm going to stop here, and we're going to meet again on the 21st from 1 to 5. Email me with any question, and I'll be glad to help you. Okay, thank you very much. Be safe. Try to do your best to be safe always, and I will do all my best to stay safe also, because I need to stay healthy, and I wish the best to all of you. Good night, everybody. Let me see if I can do something here. Good night, everybody.